So let's start with the script 2A in our flood mapping module. What we've done so far is we were trying to map floods that occurred in this particular district between these dates. So we start with Sentinel-1 collection. We filter to that particular district, and we apply a different start and end date for before and after collections. And finally, we find multiple images. We need to display them, create images. Since this is SAR data, that doesn't have outliers. So you can do mosaic. That means whatever is on top, just consider the latest pixel on top and just give me that image. Or you can do mean. Either is fine. There's no big difference between those. So you can do mean or mosaic, and you can create an image from whatever images you found for the duration. And we have the before and after images. So this is what we've done so far. You can see this is what the images look like. So this is the before image, and this is the after image. You can see more black here. This is all the flooded regions. Now we want to detect those pixels which are flooded and then quantify that. But first, let's learn some more techniques about how to filter this data accurately and how to visualize them better. One of the things about Sentinel-1 is normal satellite images. Satellites capture data only in one of the orbits, so typically the descending orbits. And Sentinel-1 can capture data both in descending and ascending orbits. And since the images are looked at from the slant, so from an angle, this same region, if it was captured from a descending orbit, it will be looking in this direction. If it was captured from the ascending direction, it will be captured in this direction. That means you're looking at the same region from two different angles. And if you have one ascending image and one descending image, they'll be very different because they're looked from a different angle. And one of the things you have to make sure that whatever images you have, they're collected from the same orbit. You cannot mix images that are collected in different orbits. So we'll have to filter out and select images from the same orbit. So let's learn how that works. This is a diagram showing how Sentinel-1 collects data. There are multiple parameters here. So this is the region, the red region is where you have a revisit time of 6 days. So this is where all satellites are collecting the maximum number of images. Rest of the world in green is 12 days. All the lines which are in this direction, right? These are ascending orbits. The ones that are in this direction, they are descending orbits. So if you're in a region where you have collects from both ascending and descending orbits, you have to make sure you select images from either of them. You cannot mix that. This region that we're trying to map for this particular example is here. And here you only have descending orbits. So that's why we can say this doesn't matter, or we can say select descending orbits. But if you're in another regions where you're trying to map floods and you have both orbits, you need to filter out data from one of the orbits. This is also showing the different modes. You can see that most of the world is in this IW mode. There are certain regions which are in kind of EW mode. These are in red. Some of the islands are in IW mode, and so on. So again, when you are in a region which have both, you have to filter out and select only a single mode image, because the two modes will have very different backscatter. You cannot combine them. So we'll go and update our filters so that we always get images which are comparable. So most of the world is collecting data in this IW mode. So we'll say, select the data collected in IW mode. I want my orbit to be descending. This ensures that if you're in a region which have both ascending and descending orbits, you select only one of them. If you take this code and change your region, make sure you change this part. Make it ascending if your region is only ascending images. If you do descending and you get 2 images, or you get no images, try ascending one. See if you get more images. Because depending on time period, you may have only ascending images in that period. Some other filter just to ensure that you get homogeneous images. So we'll just say, give me all images where the resolution is 10 meters. And we have the VV and VH bands. That's what we need. Most of these are not needed for most part of the world. But again, you have a standard filter code that you do for a Sentinel-1. And all of this is to ensure that you are getting images that are homogeneous and comparable. And we'll just need the VV and VH bands for our collection. So we've done this. Okay. And now when we've done this, we should now get images which are in this collection are homogeneous and comparable. So we can do mean or mosaic and compare them with each other. We have selected the VH band here, and that is just one band of information. We have VV band also, right? That has got some more information. Can we visualize all of the information that is in both VV and VH? This is useful where you want to visually interpret the image. You have more information. If you had 3 bands, you could put them in an RGB image, right? You can, similar to how we do for Sentinel-2, we can put band 432 and create an RGB visualization. But here you have only VV and VH. So how can we create an RGB visualization which takes information from both the bands and create something? So let's learn some of the advanced visualization techniques. So we have the same image. It has got some information in VV band and VH band. If you want to create an RGB image, we need 3 bands. So one of the things that people do, which take the third image, which is the ratio of the VV and VH bands. So you take VV divided by VH. And it has been found in a lot of experiments as well as scientifically that the ratio of VV and VH closely relates to vegetation. So people use ratio VV over VH to track vegetation in absence of optical imagery. So you're tracking, say, NDVI, and you have a gap in observation. The NDVI correlates closely with the ratio of VV and VH. So that might be also useful to compute. And you can now take VV, VH, and the ratio of VV, VH, put them all together in a 3-band image, and you can create an information that has got all the information that you have in your image. This is useful for mostly visual interpretation. And a lot of SAR imagery is interpreted visually. As I mentioned, a lot of people use it for defense, for interpreting features. So now you don't want to interpret only 1 band at a time. You can put all the information, you'll have more information that you can use to interpret. So let's learn how we can create this RGB composite. So we have this before and after images. Both have the VV and VH images. Let's first add this ratio band. Right now, if I print an image, this image has 2 bands, VV and VH. I want to add band VV or VH. Let's write a function. I'm going to write a function. This will take an image as input and will compute the ratio of VV or VH. And this one is just, you select the VV band, you select the VH band, and you divide them. So we say select the VV band, dot divide, select the VH band, and we'll rename that as VV over VH. And we'll return the image dot add bands ratio band. So simple function that once you run this, give it an image, you'll get you an image back with 1 additional band. So let's say add ratio band. We'll call this function on the before image. And let's see what we get. So we had a 2-band image. We ran this function, and now we get 3-band image, VV, VH, and VV over VH. So we have 3 information. We wrote a function because we can now do the same for an after image. We don't have to kind of write a code for that. We have a function that accepts an image, so we'll just send it the after image as well. So now we have before and after images. And since they are 3-band, we can display them as RGB. Let's try to visualize them. Now, let's say we've used this for VV and VH, right? So -30 to 0, that's our visualization parameters. Let's use them and see how it looks with our RGB image. To get something, let's inspect some pixel values. If I inspect the pixel value, you can see my VV and VH values are between -30 and 0. But when you take the ratio is like 0.4, 0.5. So now my visualize parameter doesn't work. I don't visualize my VV or VH ratio effectively. So again, this is a lesser known feature of Earth Engine. In all other software, you can define per band vis params. Saying band 1, these are the vis params. Band 2, this is the vis params. Band 3, these are vis params. If you read the docs, you can give a list of values for min and max. And that will be used per band. So if you have 3 bands, I say band 1 min is -30, band 2 is -30, band 3 should be 0. max should be 0, 0, and 2. So now this will be applied per band. And now you'll see that there'll be contrast edge applied per band, and you'll see a much nicer visualization that utilizes the full information for all these 3 bands. Now, when you zoom in, you'll see information from VV, VH, as well as the ratio. And you'll see all of this in a pretty high contrast. This kind of thing is useful where you are creating a map and you want to display all the information that you have, or you are digitizing the features or trying to interpret visually. Doing this kind of RGB composite is a good technique to get all the information in a single image. I want to explain one more technique for RGB visualization. Here we took a single image. So it was either a before image or an after image. We took the VB band, VH band, and a ratio band and created one image. So if you want to compare and see where the changes were, you need to create 2 such images, and then you can see them side by side and do it. There is another technique, which is using this technique of creating 3 different bands, but it is used to display change directly. So you take some bands from before image, some bands from the after image, put them together, and you can see all the changes in a single image. So to do this, you can do something like this. You take the VH band from before, you take the VH band from after. So you can see in the before VH band, there are no flooded areas. And after VH band, we have flooded areas. And you put them together. So you create an RGB composite where the first band is the before VH, second band is after VH, and third band is before VH. You need 3 bands at least to create a composite. So we just repeat the before VH band. And now when you create this image, suddenly you can see the flooded areas much more clearly. Right? You can see all the stuff in purple is flooded. If the stuff that went the other direction, you'll see them in green. But here, most of this went as flooded. So you can easily detect where the changes happen. So this is called a change visualization, where you're taking 1 band from before, 1 band from after, and putting them together in an RGB composite. So this is also very effective. If you look at the ESA's flood alerts, you go to the website and download the published flood alerts, they give you an image like this for visualization. So again, if you're publishing data, creating an app, or creating some report, this is a very effective visualization to say, hey, this is what the Sentinel image shows as changes. Let's try out this in an exercise.